All right, so now we're going to go to, I promised you 6 properties. So here's the other 4. They're basically all essentially at the top of our thing there. And what we have, right, is one of our properties deals with what happens when I take the log, any base, right, of a product. Well, the theory is that I should be able to take the log of one factor and add to it the log of the other factor. So it becomes the sum of logs. So the log of a product becomes the sum of the log of their factors. Quotient, if I have the log of a quotient, again, any base, then it's basically the logarithm of the numerator minus the log of the denominator. And then we have the exponent, the log of an exponent. What it seems to be happening is if I take a log of an exponential expression, notice the bases are different. If the bases were the same, we'd be back to the inverse properties we just learned. But since these bases are different, what I can do is basically take that power, move it out front, and multiply it by the log of the base, log base A of the base. There's a change of base formula that I'm going to talk about a little bit later. I'm going to focus on these big 3. All right? And before we move to technology to get a feel for them, let's just go ahead and kind of see that this should be the case, right, because of what happens when we are basically working with exponents. For this first one, back in exponents, if I had a to the m and I multiplied it to a to the n, right, the rule was we kept that base and we added exponents. So if we're going to do that exponentially with a product, right, it makes sense that we should be doing something similarly with the logarithm of a product. We should be breaking it up into a sum. All right, and then we also learned that if I have a division, right, that we kept the base and we subtracted exponents. So logarithmically, we should be doing something similar, right, since it's the inverse. So the log of a quotient becomes basically the sums of their logarithms. All right, so those ones kind of follow suit, and then this one follows because of that one, which I'll share with you in just a moment. But now that we've kind of gotten a feel with them using our exponential rules and seeing that they have the kind of a logarithmic counterpart, let's just go ahead and mess around technology to get used to it. Because my technology, log base 10 is on the calculator and the natural log is on the calculator, I'm going to do my investigation with those. And then it just basically follows suit because the properties are for any base. So let's just pick a number, right? How about we pick the number 16? All right, when I look at the number 16, right, let's first take the log of it. And when I take the log of 16, right, oops, let me clear this out. So when I take the log of 16, what I get is 1.2, right? So this is roughly 1.2041119983. All right, so that's the power that I raised 10 to get 16. Log of 16 is that number. But using these properties, right, what I can do is rewrite 16 as a product. There's lots of ways to write 16, right? So this is the log of 8 times 2. So under the log of a product rule, this becomes the log of 8 plus the log of 2, right? So going to my calculator and typing that in, right, the log of 8 plus the log of 2, what we should do is get the same decimal approximation, and we do. There's more. 16 is also 4 times 4, right? So if we use the same rule, right, the log of 4 times 4 should be the log of 4 plus the log of 4. And so again, using my calculator, the log of 4 plus the log of 4, right, equals the same thing. So are there other ways to come up with 16? Yeah, all right, but it turns out that we've kind of, again, just with technology, have kind of verified that if I have a product and I break it up into its sum of logarithms, I get the same result. We could have done this with the natural log as well, right? What's the natural log of 16? Well, the natural log of 16 is going to be equal to, it looks like 2.7725888722. So again, using the same terminology, how about I be different? Well, I'll be the same. what's the natural log of 8 times 2? Well, by our property, that's the sum of the logarithms, right? Natural log of 8 plus the natural log of 2. So the natural log of 8 plus the natural log of 2, right, equals 2.7258772. So basically that seems to be verified. All right. And so what about the quotient, right? This is all product. What about the quotient? Well, again, let's just think of ways we can write 16 as a quotient, right? One of the ones that comes to my mind is writing that as 32 divided by 2. And so using our quotient rule, right, this should be the log of 32 minus the log of 2, right? And when I go to my calculator and when I type in the log of 32 and I take away the log of 2, what we get is the 1.241898, right? So it basically, again, seems to be working the way that it should, all right? And so we kind of verified that. A natural logarithm rise, right? Let's think of another way to write 16. I think 16 also would be 48 divided by 3, right? And so this becomes the natural log of 48 minus the natural log of 3. So if I write that in here, the natural log of 48 minus the natural log of 3, what I should get is that same, decimal of 16, right, which is 2.7588722. All right, so again, using my technology, that quotient rule seems to be in play. As far as the exponential rule goes, 16, right, we can write it a couple ways, right? Let me go ahead and just use the logarithm. 16 is 4 squared. So using this property, right, what I can do is move that 2 out front and multiply it to the log of 4. So looking at that, right, we're going to take 2 and multiply it to the log of 4, and lo and behold, what we get is the 1.2418989. Another way to write 16, that's the log of 2 to the 4th power. So using this log of an exponent, I'm going to move that exponent out and multiply it by the log of 2. And so 4 times the log of 2 gives us 1.2419888. And again, the natural log would be the same, but I think I've just kind of, I'm getting a little lengthy, but hopefully I've kind of verified what we have seen. So if we take the log of a product, it breaks up into the sum of the logarithms. If we take the log of a quotient, we basically subtract the log of the numerator minus the logarithm of the denominator. And if we have the log of an exponent, we move the exponent out and just take the logarithm of the base. So again, we kind of see that that makes sense in terms of exponential rules that we learned way back in the day, and it seems to be working with the technology. If I take my number and break it up in a product, as a quotient, or as a exponent, everything seems to be falling in line. All right, the last thing I want to mention here is this is something very, very unique about the logarithmic function. This is a function name. So just putting log by itself is meaningless. As a matter of fact, if I just type log and enter, I get an error, right? It's a function name, kind of like f is a function name. In order to make it meaning, I got to put something in it, right? So f of 2 now has a meaning. Same thing with log, right? Now it has meaning. I've given it an input. It can now tell me what the output is. And why this is significant is because no other function does this, right? If we had f of 2x, we never ever said that this is f of 2 plus f of x, right? But if I talk about log of 2 of x using our product rule, this is log 2 and log x. So we can play around with our function name in these manners. It satisfies a product rule, it satisfies a quotient rule, it satisfies an exponential rule, and no other function, no matter what name we give it, does the same thing. Something very, very unique to the logarithmic function. All right, so now that we've introduced ourselves to the properties, let's go do some homework problems where we basically use them in a lot of different environments.